Our next job is to find what's the total time at the maximum height and also the total time to reach your landing position. From our previous analysis of projectile launch horizontally, you use the value of the time by using the equation 2 delta y over g. But in this case, we do not know the value of delta y yet. Therefore, we're going to use our knowledge of the special conditions that we have when it reaches the maximum height Vy. We also need to use the value of the Voy that we have solved in the separate video. So now we have to get our list of equations, and if you look at the vertical motion along the y-axis, we know that we have this equation that includes the time and the initial velocity and the final velocity. So at the peak, so we're going to use this for our t up, and this is going to become, we know that it momentarily pauses or stops. Therefore, we can use our initial velocity y, which was 6.1 meters per second, and you know already the value of gravity, which is 9.81 or 10 meters per second for simplicity. Then we will be able to know this value of delta t. So if we rewrite that equation, that's going to be Vy equals V initial y minus gt on the up, which is your maximum height. So this is 0, and this is 9.1 meters per second. So by manipulating this, we have to move this first on the other side, so that becomes Viy equals negative t up times g. So the negative and the negative cancels out, and if we divide both sides by g, then we get our t on the peak or the maximum height to be Vi. If you want to use the original equation, sine of the angle over g, then that's going to be our T max. So you plug in the values. This is going to be 6.1 meter per second divided by 9.81 meter per second, and that's going to give you your time in seconds. This is approximately 0.6 seconds. But remember, this is only from the starting point to the maximum height, not the total time to the landing position. So going back, this will give us a value of 0.62 or 0.6 seconds, and therefore we can now have our T maximum or T landing, which is just the double the time from the start to the peak, because they are symmetrical and we assume that there's no air resistance. So the total time will be 1.2 seconds. So we're almost done. We are on the last step. You want to find out what is the final velocity on the landing position, both in the x direction and in the y direction. Graphically, this is very easy because we know certain conditions both on the x and the y. So if you take a look at what's happening, if you recall, the green vectors represent your velocity along x, and what you think is happening? You're right, it's constant. Therefore, whatever was our value on the x, which you remember in the previous slide was 7.2 meters per second, then in the landing position, it doesn't change. So it must be 7.2 meters per second again. And then in the velocity y, if you follow the red vectors, it's gonna be the same in magnitude as your initial, which is 6.1 meters per second. The only thing that has changed is its direction. That's why we have there the negative value. So the negative means downwards. Mathematically, however, you can solve this Vy by using the equations. So if you look at our equations, so let's take a look at our list of equations. So if you use this equation, this means that this is your final velocity at the landing position. We know this initial velocity along y, which is 6.1 meters per second, and we know also our gravitational acceleration, 9.81 meters per second. And you've got to figure out that this time is your total time for landing, which we calculated a while ago as 1.2 seconds. So you should be able to arrive at a value of Vy to be 6.1 meters per second also. The other equation that's possible is this third equation. It's again going to give you the value of your Vy at the landing position, or the velocity component in the vertical at the landing position, by using this equation. We know that we have calculated that one already, and the delta y here means how much is the change in position starting from 0 to the landing position. But since we know that they started at the same height and landing at the same height, then this becomes 0. And this equation boils down to be just equal in magnitude, but the square root function can give you either a plus or a minus. So we have to choose the minus sign since your object is moving downwards. So there you go. We already have answered the Vox, which is equivalent to the Vx final, and we also have gotten the value of Vy, which is the velocity in the landing position in the vertical component. But our problem does not really end there, because we have to know the total velocity. Okay, and this is our total velocity. So we've got to find out what is the magnitude as well as the direction of this landing velocity. And how do we do that? To find the velocity at the landing position is that the opposite of what we did in the initial velocity when we find the component along x and along y. In this case, what we know is the final velocity along x, which is 7.2 meters per second, and we have a velocity along y, which is a negative 6.1 meters per second downwards. And in order to do that, we are going to draw like a triangle again, but in this case, we have to follow the rule for addition of vectors. So we have to do something like the Vx first, and then the Vy, and then we connect the starting point to the ending point as our resultant vector, which in this case will be our V. So this is our Vx, and this is our Vy, and this is going to be our theta. Because we have learned that addition of vector is cumulative, then we can also start with a velocity y, and then from the tip we do head to tail method, and then that's going to be our Vx. So you see, it doesn't really matter which goes first, because addition should be the same. So we now connect our first and last vector to be our total vector in the landing position. As you can see here, this must be the same as this one. And how do we solve for that? We just use the Pythagorean theorem. So V becomes square root of Vx squared plus Vy squared. And so in this case, we have, okay, I will omit now the units because it's going to be consuming space, plus 6.1 quantity square, and that should give you a value of 9.5 meters per second. Does that sound familiar to you? Yes, because that is basically our starting velocity, where we resolve it into 7.2 and 6.1 component. Again, this is just your magnitude, okay? And remember, vectors need both magnitude and direction. So the magnitude can be taken from the Pythagorean theorem. And how about the angle? Okay, now if you're going to use this triangle on the bottom, do not use this angle, but use the complementary angle, which is from the horizontal. So this is a better choice because your angle is already inside, or it's with respect to the horizontal. So if you do this, since we know this value as your, again, what's the location of your Vy with respect to the angle, this is our opposite and this is our adjacent. And to find the angle, what function will you use if you know the opposite and the adjacent? It should be tangent. Okay, so tangent is opposite over adjacent. So in order to manipulate this, we'll have to use theta must be the inverse tangent, or we call it arctangent, of the opposite side, which in this case is our Vy. So that's going to be our Vy over the adjacent is our Vx. So if you plug this in your calculator, this is going to be 6.1 meter per second over 7.2 meter per second. So the units will cancel, and you're gonna see that your angle must be, of course, unitless. And make sure that your calculator is in degree mode, otherwise you're gonna get a different angle. And you should be getting 40 degree. Okay, so what's the meaning of a 40 degree? And by the way, your 6.1 is negative, so what's the meaning of a negative in the 40 degree? This means that it is below the positive x-axis. So there you go. We found the direction, this is our direction of the total velocity vector at the landing position.